Okay, let's have a look at these ones. So today we're looking at graphing more complicated rational functions. First up, we're looking at the basics. What is the domain of a rational function like this one, and what are the vertical asymptotes? So the vertical asymptote is created by a divide by zero here in the denominator. So to find the vertical asymptotes, we simply take the denominator, set it equal to 0, and solve. This gives us a vertical asymptote of x equal to 1. But the domain is also quite simple then. So the domain is going to be x is applied over everything but -1 for all real numbers. It's that easy. Let's try this one. So again, vertical asymptote is given by x plus 1 equals 0, which gives x is equal to -1. So the domain looks fairly similar. What are going to be the vertical asymptotes of number C? What will the vertical asymptotes be, please?
Those are -1.
Why?
Because first we make it into like a quadratic, and then we make it equal to 0, and then we solve for x, and it gives positive.
Hopefully you didn't go the long way around doing that, of expanding the brackets and then re-putting them back in again. Once it's in factored form, it's pretty easy to see them, isn't it? But yeah, in order to find the vertical asymptotes, this is actually a quadratic. So when you say you make it into a quadratic, this is a quadratic equation. This is a quadratic equation in factored form, not in standard form. It's in factored form, but it's still a quadratic equation. Very easy to solve this form of equation. We can see that x is equal to 1 and x is equal to -1. So this one has two vertical asymptotes. This one has two vertical asymptotes. The domain has two excluded values. So when we want to know what is the excluded value, this is the ones that we're excluding from the domain. So watch out for the word excluded value. So the excluded value is the value that's excluded from the domain. This one's going to have two excluded values. Otherwise, it's applied over all real numbers. What do we think about this last one? We want x squared minus x minus 6 is equal to 0 for the vertical asymptotes. If you haven't done it yet, practice factoring this right now. If you haven't already done it yet, I'm going to give you a minute. Make sure you practice factoring this one right now. This is going to be x squared plus x minus 6. Your signs are wrong. One of these, a value that's not that's excluded from the domain. Excluded means to not include. I can't think of another way of putting it. Oh, you want a pink tip for success? There you go. See, it's supposed to be there. Can you factor these? So let me just come around with a random. not an equation anymore. You've gone from equation to an expression. I think that's really funny. Okay. It should be it. Once we get this, I can't see you going wrong after that. Yep, looks good. You know, nothing. This, when you expand it, is going to give x squared plus x minus 6. Okay. Why is the equation an expression? This is an equation. This is an equation. This has no solution. It doesn't have any solution. What are you missing? Otherwise, it's just an expression. And look, just how much do you find onto this page here today? You're very economical with your page. It's a bit much. There's no white space. You sharpen your pencils. No. Where am I? I'm looking here. This is a very long process. Where am I supposed to?
I will start to understand. It's weird. It's weird.
I'm just not sure.
So far, it's good. All right. So this is going to give us x minus 3, x plus 2 is equal to 0. It's going to give us 2 asymptotes. One at x is equal to 3 and one at x is equal to negative 2. So the domain is this. Can I ask you to graph this on your calculator now, D? Can you graph D on your calculator? Oh, can we do C and D? Start with C. Have a look at how one of these look. Start with C. Have a look at how one of these look. Yeah. Graph the rational equation, the rational function C. Do this one first. We've seen the other type, but have a look at one of those. Yes. So let's start by graphing this.
Why are there 3 different There are 3 different
2 asymptotes. Can you see the 2 asymptotes there? You can see it's an asymptote. If you try and trace it, if we try and trace the graph, normally we can trace the graph. If you try and trace it at 1, it will only do that if this is an asymptote. Otherwise, it will trace. Yeah, you want to change your because of this. It's so hard. And your scale. Change your scale so you can see better.
You just graph.
Yeah.
But you should, because there are 2 asymptotes.
But do I have to be in the group? And to change the
No, we have to
system.
minimize the graph. No,
Otherwise, do it manually.
There should be other.
X minus.
But this is wrong. There are two asymptotes for it. No, it's not. Correct. That's the big review.
All right.
Yeah, it is correct.
So if we sketch this one, we should see the asymptotes. Follow me through on the calculators. I'm just going to show you some skills for this. So we are here. Press on, have a nice new calculator. Let's save that. Add a graph. So if we want to put this graph in, press Control, divide, get your quotient, x minus 4. And then we want a couple of brackets on this one, x minus 1, close bracket, x plus 1, close bracket. It's going to look like this. We can see the two asymptotes. If we want to find the asymptotes on this one, we know that they're at 1 and minus 1. You can visually confirm that. You can only confirm, you can't find them so easy with this routine. But if you try and type in a trace point for x equal to 1, you can sort of see, all right, yeah, it is. And it gives you a visual confirmation. If I try and trace any other point, it will give me the value. But it won't for that, it can't. It's like, what? This is undefined. You see here in the bottom right corner, it shows at 1 it's undefined, which means there's an asymptote. If we try and trace it at some other point, let's say 1.001, basically at 1, it will actually find you a value. So it's the only place it won't find you a value is on an asymptote, and you visually see it. Let me just put my calculator back into standard settings. So that's the first one. We can see two vertical asymptotes where we're expecting them to be. So everything is good here. We can see the horizontal asymptote. The horizontal asymptote is going to be at y equals 1. The horizontal asymptote is going to be at y equals 0. What am I talking about? You can see it happening there. Okay, let's have a look at D. Let's have a look at D now. We're expecting two asymptotes here on this one. We're not seeing two asymptotes. We thought there's going to be one at x equals -2 and x equals 3. So just tracing the graph trace, type in -2. We see there's a vertical asymptote there. It's undefined. Here in the bottom right corner, that is a vertical asymptote. What's going to happen is we try and trace it at 3. So I try and trace the graph at x equals to 3 now. I press enter. It's undefined at this point. Undefined, but there's no asymptote there, is there? This is true, this is not an asymptote. What's going on here? What's going on here? Any ideas?
Is it because the numerator is also going to be 0? If x equals 3?
No. They're gonna kind of in a yes and no. But let's have a look. What we're going to do is we're going to do a bit of limit analysis and looking at the end behavior. So what we're looking at here is we're going to use our calculator to examine the behavior of f of x near these 2 points, see what the values are. So we have the function in now. So get your calculators in your hand. Make sure you have this function typed in. I've got it typed in on my calculator as f2 at the moment. So mine is f2. Mine is f2. I'm going to go to the calculator page here, like this. Make sure you've got your calculator in your hand and you're practicing this routine. This is an important routine where we look at the behavior as we approach a particular point. So a few of you have seen me criticize you when we do equation solving, and I use the implication symbol. Like this. So when I write like this, sometimes you've written what you think is something similar, and you've used an arrow that looks like this. And I'm like, no, you can't use that arrow. These two symbols are not the same, they're not synonyms. So this symbol here, we're going to see it today what it's used for. This symbol means approaches. It means approaches. The correct symbol for the implication looks like this. So an implication is made with like an equals sign and then a greater than symbol there at the end. And this is the implication symbol.
Can you use like three dots in the triangle?
Yeah, therefore. But typically used as you're moving into a conclusion building from several statements. If one statement directly implies the next statement, it's better use the implication. If a whole series of calculations and investigations then and you're moving into your conclusion, you normally use the three dots for therefore. All right. So what this symbol means is approaches. So what we want to do is we want to look at f of x. What is the value of f of x as x approaches -2? Now, so -2 on this graph, if we trace it, -2, put that in, there's the asymptote. So -2 is here at the asymptote. So the value at -2 is what? It's undefined. So f of -2 is undefined. So if we wanted to find out, use function notation, what is f of -2? The correct answer is D and E. Does not exist. So if we wanted to find what is f of -2, we can say this does not exist.
So, what does the little minus mean?
I'm getting there. I'm getting to this. So I'm heading towards these two symbols here now. So we are going to approach -2 from the left-hand side first, and then we are going to approach it from the right-hand side. So what that means is I'm moving along the curve in this direction and seeing what the values are. So as I approach the curve from the left-hand side, that's this one. As I approach the curve from the left-hand side, I have to put in values that get closer and closer to -2. So I can start at -2.1. -2.1 is some value on the left-hand side of where -2 occurs on the graph. And I can find the value here. Here it's 12. Let's see what happens to the y value as I get closer and closer to -2. So if I want to put in something which is closer to -2 than this value, what would I put in?
-2.0.9.
I can take a bigger step. You're correct, your answer is correct. Let's take a bigger step closer.
2.02.
So let's take -2.01. I'm closer now, aren't I? I've moved a lot closer, up to 102. Let's do it again. Let's get even closer now. What should I do to step closer? Go step.
-2.001.
-2.001. Oh, 2.001. What number is this? 1E3. What number is this? That's 1,000, more or less, rounded to 3 significant figures. So it could be 1,002, and it would round it to 1,000. If you don't want your calculator giving values like that one, click Document 7.2 and change it out of float in 3 into float. Press Enter. Yeah, it's 1,002. It's because it was rounding to 3 significant figures. If I want to go one step closer, I will go to negative 2.0001. Where are these values heading? To infinity, to positive infinity. So we say, what this sentence is going to say, it says, as x approaches negative 2 from the left-hand side, so let me use my highlighter pen through this. As x approaches negative 2 from the left-hand side, f of x approaches, and then I write in infinity. Infinity. Let's have a look what happens as we approach negative 2 from the right-hand side. So we want f of negative 2. What would be something suitable to the right-hand side? Negative 1.9. Sounds good to me. Negative 1.9. We're at minus 8. Let's move closer. If we want to move closer, where do we go now? Negative 1.99. That's closer. There, we're going up. Let's go closer still. Negative. Yeah. These are hard questions. We're going closer and closer. One more time. One more time. 1.999. Can you see the pattern?
Yes.
Where are we heading?
Negative infinity.
This is heading to negative infinity. So as we approach these two values, as we approach negative 2, the function will either approach positive infinity or negative infinity. This behavior is asymptotic behavior. So we see it's heading towards an asymptote and shooting off in 2 different directions of this asymptote. And then we can sketch the graph. So with these type of calculations, you can then sketch the graph. Let's have a look at as x approaches 3. Because when we looked at the graph, what was happening at 3? When we looked at the graph, it looks like it goes through for 3. So here at 3, it looks like it goes through it, doesn't it? There's no break in the graph on the calculator. But then when we try and trace it at that point, at 3, it tells us no, this value is undefined. And this is correct. So f of 3 does not exist. It's not in the domain. F of 3 does not exist. However, let's do the approaching. So what does this say? What does statement C say?
As x approaches 3 from the left-hand side.
Perfect. As x approaches 3 from the left-hand side. So we'll do that. We'll approach 3 from the left-hand side. So what will be a good value approaching 3 from the left-hand side?
2.9.
2.9. Okay, so that's 1.79-ish. Okay, let's go a little closer. Let's go 2.99.
Just gonna put these on your desk, sir.
Oh, thank you. They can't be gifts to people in this room. No, they're not. For my crew.
Yeah.
I'm like, these guys aren't late.
No.
Maybe Zoya. Also in my crew. All right. Which value are we heading towards this time? Let's keep going a little bit more. Let's go quite a few more. What value is this? This is 1.8, isn't it? This is heading towards 1.8. We see it getting closer and closer to 1.8. So this value, as x approaches 3 from the left-hand side, f of x approaches 1.8. Let's see what happens as we approach it from the right-hand side. So from the right-hand side, we want 3.1. Let's do a few more. 3.0. 3.01. And then a couple of extra zeros this time, 3.0001. What value is this approaching? 1.8. Now, so the limit value at this at 3 is going to be 1.8. But there is no f of 3 is not 1.8. F of 3 is not 1.8. We are approaching 1.8 from both sides, and then we get a hole. Literally, that's what happens. We get a hole. Let's have a look. Why? Why do we get a hole? So have a go at rewriting this expression so that the numerator and denominator are factored. Does this form of the function explain the behavior of the function at x equals 3? Who's ready for some red headed shade? Or success? That's why. Red headed success, you think? Yeah. Let's have a look. Well, this isn't a function anymore. It's just an expression. And it's not even the same function.
F of x.
It's not even the same. Here we have it. What have we got? 2x squared.
It equals f of x squared cubed. I need this. Just write the function.
So can you check how to calculate?
X plus 3 and x minus 3 don't cancel out. The equal one. You don't cancel out.
Are we doing this?
Yes, right, but they don't cancel out. They just stay. Just. I don't know. Only say when values cancel out.
Enough success over there? We get a cheating. Outside. Not easy. No, this one's
How do you get in?
Okay, let's have a look. What have we got here? So we need to play around and factor the top one a little bit. This you need to work with in your rough notes. So in your rough notes is we want 2 times minus 9 gives us minus 18. And then we want to consider the factors of 18, and we're going to choose something on the lines of minus 6 times 3, because minus 6 plus 3 is equal to negative 3, which is the middle term. So we're just playing around with it like that. And then we still need to play around with it a bit more. We've got 2x squared. Which way around did I like it best? I like the minus 6x best. Let's do minus 6x plus 3x minus 9. This is equal to, and then we can factor out the 2x from each one. This gives us x minus 3. Here on the second one, we need to make an x minus 3. So we have to factor out plus 3 on that one. And this gives us 2x plus 3 is equal to x minus 3. Now, let's take care what we write when we write this function and how we use the equal sign. So f of x is equal to 2x squared minus 3x minus 9 over x squared minus x minus 6. This function is equal to 2x plus 3 x minus 3 over x, and here we want plus 2 and then x minus 3. These two functions are the same function. These two functions are the same function. Why do we have no asymptote at x equal to 3? Discuss with the person next to you. Why do we have it?
There's not the same thing as a whole. There's a whole lot of
Okay, so a little sketch. This function here, f of x. This function here has a vertical asymptote. Sorry, let me improve my graphing skills a little. So this function is of axes. What's the vertical asymptote for this function? We got a vertical asymptote here, haven't we? When we graphed it on our calculator, it looks like this. So, what's our horizontal asymptote? What's our horizontal asymptote?
That doesn't make sense.
So this is going to have a horizontal asymptote at y equals 2. It's going to have a vertical asymptote at x equals negative 2. The function how does the function look? It was at 1.8 back. We went like this, we went like this. So the function looks like this. Almost. It doesn't. The function, if we want to draw it, has a hole in it that we can use that circle symbol for. This hole is at x equals 3. We don't see it on the calculator. We don't see it here on the calculator because the hole is infinitely small. if you think about either, how wide is the hole?
0.
It's 0 wide. We can't see that. It's an odd concept. There is no number either side of it to move to where the function doesn't exist. We have an infinitely small hole, which conceptually exists, but physically doesn't really. If you want to get into some quantum physics type stuff, this is where it starts getting fun. So we can draw it symbolically like this. We can draw it, and this is how this function looks. Now, a few of you wrote incorrectly and says that this equals 2x plus 3 over x plus 2. It doesn't. This is a different function. This is a different function. This function, please let it up just like yes.
So how do you get
There would not be a fault in If we would in the function that's this is not home, there's no.
This is g of f, this is g of x, this is f of x. These two functions look like this. Identical looking. Apart from that one as a whole, this one doesn't. So technically, you can't use the equal sign connecting these two and cancelling off the x equals minus 3's. When you cancel those x equals minus 3's, sorry, x minus 3's, you're removing the point discontinuity. You're removing the whole. So when you cancel those out, that conceptually is why we're getting the point discontinuity, but you can't remove it without making a different function. These two functions look the same. To us, they look the same, but they're not quite conceptually the same. So going back to our function that we've been playing with, this one, we've got the domain correct here. This is the correct domain. The only thing we've got wrong is this asymptote doesn't exist. This is not an asymptote. So we don't have an asymptote, a vertical asymptote here, but we do have an excluded value here. The two are different. So there's two types of excluded values. There's excluded values that create a vertical asymptote, and there's ones that don't. So the ones that create a vertical asymptote are the ones that we call an infinite discontinuity. So here, any break in the function is called a discontinuity. So the ones that create a vertical asymptote, and you can find this when you do the behavior around the point and just examine what happens to the values. You see they go shooting off. They can either both, from left-hand side or right-hand side, they can either both go to positive infinity, both go to negative infinity, or one up and one down. All three possible combinations are possible, and then you draw the graph accordingly. And these are called infinite discontinuities, and this is where we get a vertical asymptote. The other one, the whole, is a point discontinuity. A point discontinuity. So a point discontinuity, you'll get a limit value at that point. You'll be able to approach the point from both sides, and it will converge on a single limit value. But you don't see it on the calculator on the graph because the calculator is drawing it very accurately. No matter how much you zoom in, you're never going to see it because it's infinitely small, the width. So to show it symbolically, we can use this circle symbol here and then label it to show our point discontinuity. Questions? Good stuff, questions.
When you got there, how did you get the result of asymptote?
I'm getting onto that now. I just know. It's easy. We'll see soon. Any other? Yes?
Discontinuities appear only on the vertical asymptote, yeah?
No. The discontinuity appears whenever you have an excluded value from the domain. So you can see them on a graph like a vertical asymptote. You can't see the point discontinuities, but you can examine them. So the functions that we're looking at, all of the discontinuities of rational functions occur when the denominator is 0. So all you have to do to find them is set the denominator equal to 0. It's your first part of your investigation of such a function. Take the denominator, set it equal to 0, find all of the discontinuities. Then examine each one, see what type they are. The easiest way to examine each one is to also factor the top and then just see which ones cancel out. So if they cancel out, that's a point discontinuity. If they don't cancel out, that's a vertical asymptote. Super easy. Super easy. Don't know why it's taken me half an hour to explain this. Okay, Gustav's question. Horizontal asymptotes. There's several types. So if we're looking at these functions, so rational functions, a rational function is defined where you have a polynomial function divided by some other polynomial function. So if we look at the degree of the two polynomial functions, it will tell us what type of horizontal asymptotes we have, if there are any. So if the degree of the one in the numerator is less than the degree of the one in the denominator, then it's going to go towards 0 at infinity. So let me give you an example of this one. Just write it up over here. So if we have something where, say we have x plus 1 over x cubed minus 1, something like this. Horizontal asymptote of this function is going to be 0. Because for any x value we put in bigger than negative 1, bigger than 1 or smaller than negative 1, the numerator is going to be much bigger than the denominator is going to be much bigger than the numerator. So as soon as x is bigger than 1, this value is much bigger than that value. And once x gets to 100, x gets to 10, this is 1,000, this is still 10. As we go towards infinity, the denominator is growing much faster. So it's much bigger effect. So with these type of functions, the only thing, as we look at the end behavior towards the infinities, it's only the lead term that really matters. It's only the lead term that matters. Now, if the lead term in the denominator is bigger than the lead term in the numerator, it will just divide everything away, so you'll end up at 0. So when the degree of p of x is less than the degree of q of x, you get y equals 0. When the degrees are the same, what you need to do to that one is to look at the lead coefficients. So if the degrees are the same, then the horizontal asymptote is the lead coefficients over each other. Not that easy. So you guys asked me how did I know it was 2. Let's go back to it now. Look, we've got second degree on the top and the bottom. So we're getting a horizontal asymptote. The lead coefficients are 2 divided by 1. That's the horizontal asymptote. Super easy. Super easy. Now, if the degree of the numerator, p of x, is greater than the degree of the denominator, all hell breaks loose. You don't get a horizontal asymptote. You get an oblique asymptote. Much harder to find. We're going to need polynomial division for that. So you'll get an oblique asymptote, also known as a slant asymptote. There it is. So when the degree of the numerator is bigger than the degree of the denominator, you'll get a slant asymptote. It will head off towards infinity. But it will head off towards infinity following a straight line. We shall have a look at one shortly. So the first two are easy. This one's a little bit trickier, but we can get there. Let's do some now. So sketch the following graph. Sketch the following graph. What is the vertical asymptote? We'll do this.
X equals
2.
So let's do a quick sketch of this. What is the vertical asymptote?
X equals 2.
X equals 2. So let's put a line in there. What is the horizontal asymptote?
1.
So we put up our asymptotes. Let's label them now. This is y equals 1, x equals 2. This function is going to look like this. What is the y-intercept going to be?
Negative 2 comma 0. No,
X
is 0.
Never mind.
1, negative 0 is 0.
Negative 1 over 2.
minus 0.5.
We just have to
Alright. So what is the x value for the y-intercept?
0.
So f of 0, negative 1 over 2. So it's going to go through here at 0, comma, negative 1 over 2. What about the x-intercepts? What is the y value on the x-intercepts?
0.
So watch what happens here. It's pretty easy too. So we've got x plus 1 over x minus 2, like this. What happens if I times both sides by the factor x minus 2?
x minus 2 is
Zero.
x plus
Hang on, let's have you shout out let's now. Let other people answer. Yeah, so instantly you can simplify this down to x plus 1. You can always do this. So you just need to set the numerator to 0 to find the x-intercepts. Because the denominator is just going to disappear. So where is it going to intercept the x-axis?
negative 1.
It's going to intercept here at negative 1 comma 0. There we go. So this time I'm doing it not using the understanding of functions transformations. I've moved off the function transformations last lesson. It's useful to understand the concepts of transformations of the functions, but this is much quicker.
So why can we graph the other sides of the axis?
Because it goes through those 2 points. And we saw last time when the characteristic point 1 comma 1 is translated, it's translated up to here, and you could find the transformations and you'll see why. Plus I just know. All right, let's sketch this one. Let's sketch this one. Axes. What's the vertical asymptote going to be? Don't shout out. What's the vertical asymptote going to be? Let's see some hands. Let's see more hands. Okay, Sydney?
X equals minus 3.
X equals minus 3. Why?
Because you have to set the denominator equal to 0.
And solve. Yeah. So set the denominator equal to 0, solve, we get x equals minus 3. What is the horizontal asymptote? Good stuff. There is none. There is no horizontal asymptote. It's an oblique asymptote. Oh dear. Let's find it.
Division.
Yeah, I'm afraid so. That's weird. Let's start again. So, we want to divide. We want x plus 3. We're going to divide x squared plus x minus 2 by that. So what do we need to multiply x by to get x squared? This gives us x squared plus 3x. Let's do the subtraction. What are we left with?
Negative 2x.
Negative 2x. Drop the negative 2 down. What do we need to multiply x by to get negative 2x?
Negative 2.
Negative 2. This gives us negative 2x minus 6. Do the subtraction.
Remainder 3.
We're going to get, what am I thinking? Oh, come on, Brent. This disappears.
Remainder 3. 4. Almost.
Okay, right. My brain's like, he's saying things and it sounds wrong to me. 2 and 6, it's got to be something, not 3. 4. We got 4. So this function can be rewritten as what? X minus 2 plus 4 over x plus 3. Function looks like this, doesn't it? So now we can sketch it. let's do, so we've got our vertical asymptote. Pretty sure this is x equals minus 3. It is. What about the y-intercept?
Negative 0.
Can we have it as a fraction?
Negative 2 over 3.
Well, all of these cancel when you put in 0. All of these cancel. Just the two constants at the end. Negative 2 over 3. So it's going to go through here. 0 comma minus 2 over 3. What about the x-intercepts? So the x-intercept, set the numerator equal to 0 and solve quickly. Can we factor that? X plus 2, x minus 1. So x equals minus 2, x equals 1. We have 2, we're going to go through here, 1 comma 0. And we're going to go through here. Where's this line? This is at minus 3, so we have one at minus 2 here. What's this? This is odd.
Are there two asymptotes?
So we need the oblique asymptote now. Slant asymptote. What is this? So what happens as we approach infinity? What will the function become?
Straight line.
Look at this function here. What happens to this term? What the hell? What happens to this term? Think about that term. What happens as we go to infinity? What is 4 divided by infinity? If you take 4 and you cut it into an infinite number of parts, how big is each part?
4.
If you cut 4 into one part, it's 4. If you cut 4 into 2 parts, the parts are 2. Okay. Try this exercise. 4 divided by 1.
4.
4 divided by 2. 4 divided by 8.
Half.
What's happening to the values? They're getting smaller and smaller. 4 divided by 100.
Negative.
It's 4 divided by 100, 0.004. 4 divided by 1,000, 4,000. 4 divided by 10,000, 4 10,000s, 0.0004. What's happening if you divide it by infinity?
For infinite.
Okay, so every time I ask you with a number, the value gets smaller.
Yes.
What's the infinitely smallest value that we're approaching to?
0.
0. 0.
So infinity.
Let's have a quick look. All rational functions are based off of our basic understanding of this chap that we saw in the first lesson. How does he look? Looks like this. What is the end behavior here? As x goes to infinity, y goes to 0. So basically, any function like this, think of this graph to understand the behavior. Think of this graph. What happens as x goes to negative infinity? What happens to f of x?
0.
Also goes to 0. Think about that. So this graph basically looks the same. It basically looks the same. It's still pretty much a 1 over x type thing. 1 over x and 4 over x plus 3, they're the same. The end behavior as we go to infinity is still going to be 0. So the function that we've got here, our f of x, this part here, as we go to infinity, that part disappears. That part will approach 0. So this function will approach the line x equals minus 2.
So the asymptote is
The,
the horizontal slant.
we have an oblique asymptote, we have an oblique asymptote, y equals x minus 2, the linear function. So let's sketch that. So x minus 2 is going to go through something down here like this. It's going to go like this. So this point here is the point 0, negative 2. This green line is the line y equals x. Oh, that's not going to draw there. This line here is the line y equals x minus 2. What's that? That's how we get this shape. Because what's happening to the function is it has to go through these points and it has to approach that line there. Let me just make this look pretty. So these are our two asymptotes. Our function yeah, I got a good one there. So this point was, what did we say it was? 1, 0. This point here, minus 2, 0. This point here, 0, minus 2 over 3. This point here, 0, minus 2. We're going to get something similar down here. I haven't really left any space for it. We're going to get something similar here. It's going to look like this. Let's graph it on the graphing calculator so we can see a prettier version. Take out your graphing calculator, add another page, type in the function, see how it looks. F of x, type in f of x.
So I have a question.
Yes. What color question?
How do I know the side is right? Like how do I know it's here or not here?
When you find these values. So if you find a couple of the values, like a y and x intercepts, then you know which side has to be. Otherwise, just put in one number. So let's say you're trying to find where it is over here. You notice it's minus 2. So just evaluate the function for minus 3. Is it above or below y equals 2? Huh?
Oh,
And that will tell
I
you.
think we didn't understand.
Some experience will tell you. So basically, if you factor out all the negatives to the front, if there are none left, then it looks like this. If there are if there's one left, it looks like that. But put a value. So let's graph it. We've got this minus 2, x plus 3. Let's add the line. What is our line? X minus 2. Let's add that straight line. You see the oblique asymptote there? Zoom out a little bit. Do some zooming out. Just want to add some to the bottom part of my y-axis. I want to add something to the bottom part of my y-axis. So on the window settings, just tap our way through to the y minimum, and let's try minus 20 down in that direction. There we go. We can see the other part there. Let's visualize it with our vertical asymptote. Where was the vertical asymptote at? Minus 3. Let's try and sketch that. There we go. That's how the graph looks.
How do you trace those?
You can't put it in. But if you know what the horizontal is, like y equals 3, you type in another function, y equals 3.
Can I use it?
Really? You don't want to do this?
Can I use it first?
And this? I guess.
So basically the front is.
Okay, let's have a go at sketching this graph.
They were served for this slot as a group on the 1 to 4 meters. What was the I don't know how I don't really observe how
Look back at them.
different division.
It's 0.
Whatever's on the top of the. So the slant asymptote.
Is the quotient.
Yes, it is.
What you get up there is the slant asymptote.
Is the Lucas
Yes. Yes. Yeah. We can graph some. So the first semester is this year and next year.
This
So we'll graphic functions. The higher level gets much harder because this is quite easy. This is standard.
algebra years.
So graphing polynomials, graphing rational, graphing radical, graphing logarithmic, graphing trigonometricals next. Those are the harder ones. Not as easy.
The graphic factors or
Yes. Yes. Have you graphed it? No, just sit there and think about flowers, meadows. Yes.
Yes.
Like before,
Absolutely communicate.
what they should do.
make a good division.
No, I'm just kidding. We need to find the horizontal asymptotes.
Using the numbers.
I mean, they're equal. Let's do it. So the numbers what are the asymptote is y equals 0.
How do you
Because the degree of q of x
It's just
to
like
x squared
what?
is bigger than x.
But then you have to check which one is.
Yeah.
Four, negative four, and one. So the horizontal.
Looking good. Where's the horizontal asymptote?
Yes, it's zero. Yeah, we have to go to like minus four. Okay, let's find y intercept and you can x intercept. X intercept is negative. One. X is negative one.
Oh, yeah,
Just use like the
so that's the y.
analyze back,
One
find
is
zeros.
one is the negative two, negative one is four. Yeah.
X is negative. Okay, so that means that is negative minus four. Y
There's y intercept zero. That is the y is equal to zero. Zero.
You graph work.
There is y intercept.
Yes, negative 1, 0.
X is 0, but
It's x. There's no x intercept. Oh,
yeah, there's x intercept.
I'm right.
Oh yeah, negative 1, 4.
Yes, it's x.
So it's
So how do you get the x intercept?
Okay.
Set the x intercept, set the numerator to 0.
X intercept for negative one. Huh? Is that-
Where's the y?
Oh, it's x plus one is equal to
Negative
zero.
one.
X minus one.
y is negative 1, 4.
Oh, yeah.
Just use the like the graph. Use like the split table and it shows everything. Oh, you never get.
Okay, 7. 7.
And then you see like all the hundred lines. Yeah, it shows all the hundred lines.
Well, isn't it not?
Where is
Because no,
Like when x is 0,
because
it shows
it's the
like
answer
check.
to it. Why is it zero?
Yeah, I think that it's zero.
X intercept.
But after it's too slow.
That's one.
But it's not y. Yeah, it is.
Alright, let me show you how to sketch this. So it's pretty tricky to see how it's going to approach the asymptotes. Let's take the function and factor it first. That's easy. We've got a factor on the top, x plus 1. And we've got x plus 4, x minus 1. So we've got two asymptotes, and it's really tricky to figure out how it's going to approach these. Put the asymptotes in, because we haven't done one like this yet. So we've got asymptotes at x equals minus 4, x equals 1. These are our asymptotes. How is it going to look? You know, we can see the horizontal asymptote as well, can't we?
0.
Why is it 0?
Because the
Denominator's degree is greater.
The degree of the polynomial in the denominator is bigger than the degree of the polynomial in the numerator, so the horizontal asymptote is y equals 0. So it's going to look something like this. And there's all sorts of combinations these can look like. They can look like this. They can look in all sorts of different ways. We've got to figure out how it's going to approach those asymptotes. So watch this bit through. Watch this bit through carefully. What I'm going to do is I'm going to do a sign table analysis. So what's interesting to us are what happens to the three factors. We've got the factor x plus 1, x plus 4, and x minus 1. All I'm interested in is what is the sign of each of these factors at different key spaces in the graph. So the way I want to look on the graph is I want to look at our critical values. Our critical values are minus 4, minus 1, and 1. I want to look at each of the factor, and I want to know what the sign is of the factor at the critical values on either side. So our first factor is x plus 1. So when is this 0?
Negative.
It's 0 here. If I'm to the right of it, will it be positive or negative?
Positive.
So all of these are going to be positive. To the left of it, will it be positive or negative?
Negative.
Negative. How about the next factor? Where is that one 0?
Negative 4 minus 4.
And we have some different people, nobody from this table, not Gustav, but we have other people doing some mumbling. Elias has done plenty of mumbling. Let's have some new people do some mumbling for me. Negative 4. To the left of it, is it positive or negative? Negative. How about the next factor? It's going to be 0 at 1. To the left of it, positive or negative? To the right, positive. So, what is the sign of f of x now? What is the sign of f of x? What is the sign of f of x here? Negative?
0.
Not defined. Not defined here because we're dividing by 0. What is the sign here? Positive. What about here? Oh, it is defined. That one's just going to be 0 because the numerator is 0, cancels everything to 0. The function is still defined at that value. It's not going to cause a divide by 0. So that factor value exists and it's 0. Tricky one, man, these ones. What about this one? What will the sign be here?
Negative.
Here? Undefined. Does not exist. And positive. All right. So the asymptotes occur where it's not defined. The asymptotes occur where it's not defined. As we approach this asymptote from the left-hand side, is the value positive or negative? Negative, so it's got to be down here. As we approach that asymptote from the right-hand side, will the value be positive or negative? So it's got to be up here. Then we go through here at minus 1 comma 0. We're going through that point there. What about this asymptote? As we approach x equals 1 from the left-hand side, positive or negative? So we're shooting out in that direction. And then as we approach it from the right-hand side, positive. So this bit's easy, it's got to look like that. It's the only way you can go from there to there. We also know that it's got to go off in this direction now, so we got to go like that. And the only bit we're not so sure about is this bit, and that'll do us. That's it for today. That's it for today. There is an IXL to play around with. That was quite easy. You don't need to do all of the, you need to do most of the questions from the homework, but don't worry about it. I'm going to try and give a little bit more class time either Wednesday or Friday this week. So I'm only going to do 2 lessons of theory this week. So I'll either spread it out over Thursday and Wednesday and Friday, or I will do it all on Wednesday and then have Friday 3 to 4. But I'll have some class time for working with questions. I think we need some class time for that. All right. Thanks, everybody. Great lesson.